Explosions are short and simple. It's the same idea of collisions, but initially we have one object. We don't have multiple objects coming together. We have one object that's blowing apart into multiple pieces. So what we get to say is that total momentum is conserved. So total momentum is again the momentum of every single piece in your system. And this is again only going to be true if it's an isolated system, but you should be able to treat your explosion as an isolated system or use the impulse approximation to treat part of it as an isolated system. Now obviously energy is not conserved, and this should be obvious that if you have an explosion happening, that's because you have some sort of source of energy. That could be a spring that then lets go, or it could be, for instance, a chemical energy source. So make sure that you don't try to use conservation of energy here. It's not. So an explosion is a little bit different than either an inelastic or an elastic collision because you're starting with one object. So let's do an example with radioactivity. Other examples can include guns, which is not my favorite topic, or fireworks, for instance, asteroids breaking apart. Here, let's do radioactivity. You start with a nucleus of uranium-238. It is at rest. Note that in some situations it might not be at rest, but you can always shift to the reference frame where it is. It then undergoes radioactive decay, breaking into two pieces. In this case, you're not told what the masses are of the two pieces, but you're told what their velocities are. Your goal is to find mass 1 and mass 2. This is an isolated system, so we get to say that our initial system momentum is equal to our final system momentum. So then we have to identify the pieces of our initial and the pieces of our final systems. Our initial system is just the initial nucleus here. And note that our initial velocity is equal to 0, so that means that this is going to be equal to 0. We then have m1 and m2, which each have their own velocities. And one thing to be careful about is that in this problem, m by itself was our initial m. So that's okay, but make sure that you're really careful about your actual notation. You also need to be careful about your signs. That m1 is traveling to the left, so that has a negative velocity. This is a one-dimensional problem, whereas normal, we're saying that the positive x-hat direction is to the right. So we have mass 1 times our negative velocity here, mass 2 times our positive velocity here. Now the goal is to solve for m1 and m2. Note that in this case I have one equation with two unknown variables. There's no way to solve this. There's no reason to set m1 and m2 to be equal. There's no reason to do that. We have to use a second piece of information. Now, if you've had a lot of chemistry, you might know that this is not entirely true, but the second piece of information that's at least true at an intro physics level is that our initial velocity is our initial mass is equal to the sum of our final masses. That we've taken our mass and we've just broken it into two pieces. Now actually in radioactivity, due to binding energy and things like that, that might not strictly be true, but this is what we're going to use in intro physics. So if you have a firecracker breaking apart, we assume that all of the mass is accounted for, unless you're told otherwise. So this is our second equation, and we know what this is, so at this point we have two equations and two unknowns. That is sufficient to solve for m1 and m2. So that's the idea of any sort of explosion. You again are using your system momentum, you're usually working in a reference frame where it's initially at rest, and then you can calculate all of your pieces.